Just to introduce our next speaker, real quick, is called Mr. Peter Wairagala Eric, and he's going to be taking us through machine translation. Mr. Peter, if you're available, I would like to really quick introduce you. He's a bachelor's, excuse me. You know, when I say the word bachelor, you're going to mistake me. He has a bachelor's degree in software engineering and is currently working as a research assistant in Makere AI Lab, Data Science Research Lab. So I would like to welcome you, Peter, to give us a presentation on your topic. Please.
Thank you so much. Thank you so much for this opportunity. I would like to thank all the mobilizers and everyone who has made this possible. So without further ado, let me just dive into it. But just let me share my screen. Can you guys see my screen?
Perfectly clear.
Yes. Good morning once more. So today I'm going to introduce a very interesting topic in the world of languages. So currently at the AI Lab, we took an interest into natural language processing, and so far we have done some interesting stuff, and I hoped it would be nice to introduce this to the world today through IndabaX. So today I'm going to talk about machine translation. Basically, as we see the word says machine and translation. So it means we are trying to use a machine to do a translation for us other than a human being. So so basically what this means is it's actually a submodule in natural language processing and understanding, whereby we try to translate a sentence from one language to another. So basically, what we call a source language is always a language that you're moving from. For example, if you want to translate from English to Uganda, which we are working on apparently. So most of the work has been to first of all try and understand the topic itself. So what I'm going to do today is just to introduce most of the aspects that in machine translation. Now, given the fact that we have a source language and a target language, today I'm going to talk about to use an example of English and Luganda. So I'm using X as my source language and Y as my target language. So for this particular sentence, I'm using a language that most people hear, few people actually, a few people don't understand it, which is Luganda, the widely spoken language in the country, Uganda today. So here, an example, we are trying to translate a sentence that says the government has constructed better health centers in rural areas, and Y is our translation. So basically what we do here is try to train models that will be doing this for us automatically. Now, machine translation actually started around the 1950s in the Cold War of Russia. So the motivation was they wanted to create systems that could try and help them to translate words that are being spoken by the other parties that they were fighting with. So what they did, they introduced the rule-based systems, which use dictionaries. So in this particular way, they used to get sentences. They tap into communications from the people they are fighting with, and they use the Russian and English dictionary to try and translate the words to their source language. Okay, so since then, we have seen a very high advancement in this particular field of natural language processing. And researchers have done some amazing work in this particular point of view. Now, the extension to our African point of view, we have started to try and do this for our African languages. Though the intentions are not to win a Cold War. Here we are trying to make sure we put our languages up there in to be very accessible to other people. Now, yeah, in the 1990s and up to 2010, the history of machine translation started with some few sorry for that, my network is a little bit not good. Started with some few techniques. For example, those people started with using language dictionaries, and also there was an introduction of statistical machine translation. Basically, this one uses the probabilities of the words. So it involves something we call the language models and also the translation models. So what this one comprises of is that the probability of a source sentence to be translated into another sentence that is the target sentence. So like what the language model helps us here is to try and my network is very terrible. The language model predicts the next word in a sentence. So as we all know, some languages have their own ways of translations, whereby we have what we call the fertility of a sentence or a word, and also we have what we call the spacious words, which these words are not, they don't have any purpose. They don't show what they purport to be. So for example, some of these sentences from another language may have more than one translations. So the language model predicts the next sentence. So we use the probabilities to predict the sentence given as source sentence. So now that's why naive Bayes rules come into play at this point in the statistical machine translations. Now, the translation models, they model how words and phrases should be translated, which we call the fidelity. I learned from the parallel data. So one thing that I've realized I forgot to mention, that before we do this, we normally have what we call as a corpus, a sentence pair. So the parallel corpus, whereby we have one language sentence, which is called the source sentence, and also the target sentence. Now, for Uganda, we use in the statistical machine translations, we use the language model to write to help us get the fluency in the language. Now, so as I think all of you can see this, the probability. Now, normally, when you train a model on a certain, when you train the statistical models, machine translation models on a data set, a parallel corpus, they produce things when you, at the prediction point, at the prediction phase, they produce what we call trigrams, the n-grams. Now, what basically this one means is that the prediction will produce several translations for every word. Now, there will be an attachment of the probability of the most expected word to be the most expected word for the particular source word that is to be translated. Now, what we do is select the maximum, the probability that is high, the word that has the high probability, and we take it to be the particular translation for that. Now, these ones, there is a lot of research being there was a lot of research being done with under the statistical machine translation models, and it's actually really amazing. Sometimes it works better for certain use cases, better than some other techniques, as we shall see. In case of any questions, feel free to interject. Yeah, now the statistical machine translation, how it works, it learns the probability, it uses the translation model. So the probability of a sentence given a source sentence from the source sentence. So we use what we call the alignment. Now, what this one does is it helps us at a word level. So we match words, we match a certain word, a source word, to the corresponding target word. Now, below, the next slide will be elaborating on this. So for the other example that we saw before, we see that some of the words in the source sentences are not appearing in the target sentence, the predicted sentence. So for example, we have the government has constructed better health centers in rural areas. So what I talked about before, the spurious words, these are words that purport in the other language, they are not there. Mostly, they are not used. So for example, here, as we can see here, there was no translation of the words there in the Luganda translation. So using the alignments, most of the times, these machine translation models try to keep the context of the sentences. And this is for the advances that have been done by researchers over the years. Now, some of the words in the source sentences translate to two words in the target sentences. For example, as we can see here, we have a word better. So it is translated in two sentences in Luganda, in two words, sorry, in two words in Luganda. So we call it one to many. Now, all these ones as advances in the languages are captured in several ways. It depends on the model that you're going to choose to use. Now, we also have what we call the many-to-many. I'll be showing it in the next slide. The alignment of the many-to-one. This is when two words, more than one or two words, translate to one word in the target sentence. Now, here, the example, I don't know whether you guys can see, the example that I have here is health centers. So health centers, it translates to amalwali, just one word in Uganda. So all this is covered, was covered in the statistical machine translation. Now, the learning alignment for the statistical machine translation is a combination of many factors. For example, we include the probability of particular words alignment, and also depends on the position in the sentence, the input sentence. So the probability of particular words having particular fertility, the number of corresponding words. For example, here, when one word is translated into many, we call that word being fertile in languages. So now, while making the prediction, we look at the probability of a word being fertile, and also we look at the probability of a word which word is supposed to be next. Meaning, we look at the alignment of the words in a sentence. Now, some of these things were solved. Researchers have tried to make some of these things very easy. Now, the statistical machine translation, it is a very huge field. I'm actually just pointing out some few things, but it's a very, very huge field that anyone can actually just decide to major in and look into, try to make new innovations in it. Now, one of the things that make it a little bit complex is that it needs lots of human effort to maintain. Now, to be able to verify that the translation of a sentence from a source language is correct, you definitely need a human effort to do the validation. Though there are several automatic validation techniques that, as we shall see in the later slides, but companies like Google, they try to find ways of making this a little bit better, because most of the times when we are doing research, we lack the human power to try and validate our solutions. Now, there is a lot of feature engineering in the statistical machine translation, given the fact that most of the times you need to actually read through all the sentences. Like you sample, in part of the pre-processing, you sample and know your points of focus. Now, the feature engineering that you may need, as we saw here, some of these things you need to understand how to handle words that have many translations, words that are fertile, and also you have to know, you have to try and find ways of handling the spurious words that are actually not existing in the target languages. Now, also the alignment. Now, this one points out a very, very huge problem, whereby some of these sentences might be even very, very long. Like, for example, a paragraph of 50 words or 1,000 or 100 words. Now, what I've seen, some of these sentences bring issues when translating. Now, for a language like Luganda that has so many weird cardinals and ordinals, it makes it very hard for statistical machine translations to give you a perfect translation at the end of the experiment. Now, one of the things that make SMT very complex is that hundreds of important details we haven't mentioned that I haven't mentioned here are supposed to be captured. What this one means is that here, since we are using a language model and also a translation model, it doesn't actually deviate very much from the rule-based machine translation rule-based machine translation technique, whereby we're using dictionaries and to be able to translate. Now here, the only advance that we are making is that it's a little bit automated. You train a language model that helps us predict the next words, and also a translation model which actually depends on the language model to predict to give you a translation. Now there is a lot of repeated effort for each language pair. Then now also this one zeroes down to the human effort. There is need to design features to capture particular language phenomena. Yeah, for languages like Uganda, there is a lot to capture. For example, you need to know how to dive into the gender bias to make your model, your translation model, not gender bias. When you give it a sentence that says she, it shouldn't say he, as those particular language things. Then also one of the things that that make SMT complex is that most of the researchers try that the best way to do it is to train a language model separately, and also you train a translation model after. So meaning you need a lot of time to do this. Though it works a little bit, it gives a good performance for several use cases. That's why most of the times it's always better to test with it before you go to test with the traditional ways of translating before you go to the new techniques. Now, after a long period of research, researchers came up with a new technique whereby we put everything in one place. Unlike the statistical machine translation, where you have the language model, you have the translation model, and then maybe you try to you create the encoder and decoder, all that stuff. The new technique, which is the NMT, neural machine translation, gives you only one single neural network that does everything. Now, for this, they used an architecture called the sequence to sequence, aka seq to seq, that involves two recurrent neural networks. Now, these two recurrent neural networks, one of them is the encoder and one of them is the decoder. Now, the encoder most of the times helps us to try and prepare the sentence that is going to be translated by the decoder. Now, as we all know, I'm sure everyone was introduced to the neural networks. Now, the encoder provides the initial hidden state for the decoder, recurrent neural networks. So the source sentence is input, and then it produces an encoding of the source sentence, which is later sent to the decoder. The decoder is basically the language model, but all this is happening in one neural network. Now, the language model generates the target sentence using a condition on the encoder. Now, Now, sequence-to-sequence models are useful for more than just in machine translation. They are actually used for many other things. For example, you can use them for text classification, summarization, code generation. Then also you can use them for pure language models, and also for topic modeling. Then speech recognition. It is actually very versatile. Given the fact that everything is in one place, as we all know, that the encoder receives the input and the decoder gives us the output. Now, the sequence-to-sequence is an example of a conditional language model. A language model because the decoder is predicting the next word of the target sentence Y. The conditional because its predictions are also conditioned with the source sentence X. So it directly calculates the probability of Y given X, which is the source sentence. Now, how to train these models? Most of the times we need a very big parallel corpus. Given the fact that we are dealing with we are dealing with neural networks, they are very high. They have a very high data hungry trait. They need a lot of data to train and give us predictions. Now, training a machine translation system. Normally, we give it a source sentence from the corpus and translates using the decoder, translates the sentence into the target language. So every word, it breaks the sentences in words. So every word the decoder gets a probability of its occurrence, and then we get the maximum probability that is returned, and we take the beta translation at that point. Now, they are optimized in just a single system, which operates end to end. So we take the aggregation of the maximum probability at each step, as I said before here. Now these neural networks, the sequence-to-sequence neural networks, have several ways of decoding sentences. There is what we call the greedy decoding, which takes the most probable word on each step. But one of its disadvantages is that there is no undoing of the prediction. Now, as we shall see in the next slide, the greedy decoding, when you predict, for example, a sentence the government has constructed health centers in rural areas, you may find that it will print all the probable words for the prediction of the word government in Uganda. So it might say governments and all that stuff. So and there is no undoing. So the final prediction might have so many trigrams and n-grams anyway. Trigrams, bigrams, unigrams. So meaning, and there is no undoing, there is no going back. The moment when you've made a prediction in the greedy decoding. We have also the exhaust. Now, to fix that problem, ideally we want to find a length of the translation Y that maximizes that particular probability that gives us the translation. Now, we could try computing all the possible sequences of Y. This means that on each step, on each step T of the decoder, we are tracking the VT, which is the possible, the vocabulary size of that word at that point, or the sentence itself. Now, I think what I forgot to mention is that in the statistical and rule-based machine translations, they look at the vocabulary of the words. Most of the times for the rule-based, it is actually manual, whereby we select we try and look at the adjectives, nouns, and all those words that are in that particular, both the source sentence, in both the source language and also the target language, which is actually, that's one of the things that makes it a little bit expensive. Now, even in the neural machine translation, there are some disadvantages, whereby it is a little bit complex to do when it comes to exhaustive search decoding. So meaning you have to look at all the vocabularies for particular words in a particular source sentence to be able to get a prediction. Now, there is another decoding technique called the beam search, which is actually most used by most of the researchers. So the core idea here is on each step of the decoder, we keep track of the k most probable partial translations, which we call the hypothesis. So the k is the beam search, the beam size. In practice is always around 5 to 10. And also hypothesis, which is y1 up to yt. So you can have several suggestions of a particular translation of a source word. So, and then get the log probability, the score. Now, mostly for several neural machine translation packages, for example, if you go into a package called the GeoNMT, the tool, so the scores are always negative, but the higher the score, the better, meaning coming back to the positive side. So we search for the high scoring hypothesis, tracking the top k, which is the beam size on each step. So the beam search is not guaranteed also for the optimal to find the solution. But it's actually better than the exhaustive search. Now, I'm just giving a high level. It may look a little bit too much at this point, but when you go deeper, you can get to understand what is actually happening when you try to do an experiment. Now, the advantages of neural machine translation is that it provides a better performance. It is more fluent, better use of context, better use of phrase similarities. Now, one of the other thing I also forgot to mention while taking you guys through the statistical machine translation is that it doesn't capture the context of the sentence. For example, the source sentence that I showed you guys before, I was talking about health centers. That health centers, meaning the health sector. Now, most of the times for the predictions, for those traditional machine translation techniques, most of them don't stick to the context of the sentence. That's why, hence the development of the neural machine translation, which actually helps to stick to the context of the sentences. And also for the other, for example, the statistical machine translation, it is very sensitive on the length of the sentences. Now, for neural machine translation, it helps also in the phrases of the words, better use of the phrases, phrase similarities. Now, it is also a single neural network, meaning it is optimized end to end. There is no subcomponents to be individually optimized. unlike in the statistical machine translation where you can have the language model separate, and then you try to create your encoder and decoder separate also, and then you combine them at a later stage. This one requires less human engineering effort. There is no future engineering mostly. I don't know whether time will be at my side, but I can try to show you this neural machine translation actually in practice. Just you don't need any future engineering. It has everything inbuilt there. Now, one of the things that I didn't put in this slide is the preprocessing. Now, some of the techniques that we use in machine translation need preprocessing of the data first. Now, in preprocessing, we use things like the byte pair encodings that help you to try and process your source sentence before taking it into through the model for training. Now, what this one does is it actually converts the sentence into a particular uniform format. But now for neural machine translation, everything is embedded inside the package itself. So you don't need to do the future engineering to go and look at these the spurious. So you can try and understand your data set before giving it to before performing the experiment, and then you can use the same method for all languages, which is not the case for statistical machine translation and rule-based machine translation and any other traditional machine translation technique. For example, if you're translating Luganda to English, you need separate rules. Then when you come to Luganda to maybe Lugishu, it will be other rules. You have to make different rules for the translation system, which is not the case with neural machine translations. Now, I'm sure I've left out so many things, but in case of any questions, feel free to write me an email and I will be able to give you resources. Now, the disadvantages, it's not that we have it all when we start using neural networks, no. Now, here's the very big problem. It is very, very, very hard to debug neural machine translation. Given the fact that we have one neural network, most of the times we have packages that you import and train, so you may not know what is happening inside, so you can't debug. And what you do most of the times is try to make your sentence fit into the requirements of that particular model to be able to train. So it is actually also difficult to control, which is not the case with the statistical machine translation or any other traditional translation technique. You can't control what is happening exactly in the neural network, or though we can tune and all that stuff, but you can't control the rules or the guidelines for the translations. Then one of the most important things that I can't forget to talk about is how we evaluate these machine translation models. Now, we use the bilingual evaluation understudy, and also there is another technique called the ROG, which is the recall-oriented understudy evaluation. Now, what the BLEU does, it compares the machine-written translation to one or several human-written translations and computes a similarity score based on the n-grams, the ones that I talked about. I didn't show the n-grams to give you an example, but think about it like, for example, when you're translating a word, he went to school, and then you have the translation comes with he, like several translations of a particular word. So that's what we call the n-grams. Then also, so what this one does, the n-gram precision, is it looks at how many words have been translated for a particular source word and makes a conclusion to take to give you whether the model is performing better or it's not performing well. Now, so also we use plus also the penalty for too short system translations. Also, that one is also it looks into that. For example, if you've given it a very long, maybe a 14-word sentence, and it gives you a 6-word translation, that one also could be a problem. So you need to look, when you're trying to fine-tune your model, you look into that. It is useful, but not very perfect. So we need the human point of view here also to be able to translate, which makes machine translation a very complex, a little bit, not very, but a little bit complex to be able to get a conclusive model that you can put into production. Now, let me rush very fast. I want to show you a little bit of the practical. Now, this particular graph shows the progress of the machine translation over the years, but this one has been done not in Africa, actually. Now, we have few languages that have been put out there in Africa. So hence the interest in doing it for Ugandan languages. Now, also, the neural machine translation went from a free research activity in 2014, leading, we can always read this, get this online, if you want to know where machine translation has come. So is the machine translation problem solved? Nope. We still have so many problems. For example, out of vocabulary words, domain mismatch between train and test data. One of the most important things to cover at this point is to look at the domain. If you're talking about education, your translations should remain in education. Also maintain the context over the longer text. For example, if a sentence is 50 words and the translation also shouldn't be more than 50 words. So yeah, then we have a problem of raw resource pairs, which is actually the Luganda English. Luganda is not, we don't have resources. There are no sentences to do the training. So basically you start from the data collection point, you prepare basically for the project, which is a little bit complex. Yes, so the research continues though. There is a lot of research that is being done and people are innovating, especially in Africa. So there is an organization called Masakane. There is a lot of work being done around African languages. You can read about them. Then some of the solutions that for the problems that I mentioned, made the problem like the out of vocabulary, the domain mismatch are covered in attention. In the interest of time, and let me just go through. So the core idea here is to use direct connection. We connect directly to the encoder to focus on a particular part of the source sequence. So, so it's like, as the word says, like attention, you put a lot of attention on the source sentence before making the translations. So it significantly improves the performance. It's very useful to allow the decoder to focus on certain parts of the source. It also solves the bottleneck problem, so allows the decoder to look directly at the source. It bypasses the bottleneck. It provides a shortcut to the prediction. So we have this, we get the soft alignment for free. There is no you don't have to look into the alignment that we looked into in the statistical machine translation. So the so the network learns the alignment itself that you provide to it. So that's just a little bit of. If you have any questions, please feel free to interject. I have a notebook here for the Luganda. So I'm using the neural machine translation. So as I said before, the neural machine translation, which is the sequence to sequence, they support a lot of natural language processing topics. For example, the sequence classification, the token classification, which is the named entity recognition, the language model fine tuning, language model, language generation. If you want to generate sentences from a source sentence also, then also then also multimodal classification. Yes.
Eric, is it possible you share the link to the notebook, please?
All right, let me do that right now. This notebook has some of my work. I think I should, I thought I would prepare a different one that will be shared. Yeah.
Can we get, I mean, before the end of maybe today or tomorrow, can we get a sample of this so that we can share to the participants?
Yeah, I will do that.
Okay, cool. All
right. Now, so to be able to use the sequence to sequence neural machine translation models, I use the simple transformers. So now the transformers actually help us to, you import the package, they help us to clone the model itself. Now, the process is always the same. We load the packages that we need, and also we load the data set. Now, one of the important things that I want to show you guys is here. As we can see here, at the initialization of the model, it is only one model, a few lines of code actually. Unlike, I wish I had my statistical machine translation notebook here. I could show you, you would see that you have several cells, code cells. For example, you have the cell for a full language model, which is not the case here. There are actually a little bit of few lines of code that you write. Now, let me see. Okay, now here, in the configuration of the model, we, as all experiments go, normally we define the batch size, and also you can, for this case, there is a parameter for defining whether you want to save the model or not, you want to save the checkpoints or not. There is also, there is one of the important configuration for the length of the sentences. Now, it's always, for the machine translation experiments, always that we can't know the length of the sentence that is going to be input into the system. So normally we define a maximum, the one that we think is maximum. For example, here I defined the length of the sentence to be 120. To be 120 for this case, to be able to cover most of the sentences. most of the use cases that have maybe more than one sentence and all that stuff. Now, for things like I defined the encoder decoder type, and also the encoder. Now, everything here is just in the package, which is the transformer. And below this code, we train the model, we evaluate the model, and also the testing, simple predictions for the testing. Now, what I have highlighted is a particular prediction for a certain source sentence that I provided to the model. Now, every word, it predicts the word separately, like from the source sentence, it gives you a prediction for every particular word. So it's up to you to post-process your prediction and get back the sentence, the sentence, and yeah. Basically, that's it. In a few lines of code, you have the machine translation system. Thank you. Back